Welcome everyone. In this video, we will be discussing the chapter 1 of Ilya Koltsov's book, Spin. In part 1.1, we are presented with fundamental concepts and operations that form the basis of mathematical structures. A set, as defined in the chapter, is a collection of objects with common properties. We learn about subsets and proper subsets, as well as operations such as union, intersection, and difference. These operations allow us to manipulate sets and explore the relationships. Moreover, the chapter introduces the concepts of maps, which are relations between sets that associate each element of one set with exactly one element of the other. We discover the importance of injective, surjective, and bijective maps, each with their unique characteristics. Additionally, the chapter highlights the significance of preserving additional features of sets through morphisms. This ensures that certain properties, such as order or metric, are maintained when mapping elements from one set to another. Moving on to 1.2. I would like to talk to you about the topic topological spaces. A topological space is defined as a set, let's call it X, along with a collection of subsets called neighborhoods. Each point in X has its own neighborhood, which are determined by the neighborhood topology denoted as T. These neighborhoods play a crucial role in understanding the properties and relationships within the set X. In this chapter, Koslov explores the fundamental properties of topological spaces. We learn that for every point in X, there must be at least one neighborhood, and every neighborhood contains the point itself. We also discover that the intersection of two neighborhoods of the same point yields another neighborhood that is the subset of both. Connectedness is an important concept we encounter. A topological space is called connected if it cannot be split into distinct subsets with no common points. On the other hand, a disconnected topological space can be divided into multiple non-empty subsets, each with their own neighborhoods but no shared points. The idea of path connectedness captures the notion of being able to travel from one point to another within a topological space. If there's a continuous path between any 2 points, we consider the space to be path connected. Simply connectedness goes a step further for implying that any path between 2 points can be smoothly transformed into any other path between the same 2 points. Another fascinating concept introduced is that of covering spaces. A covering space is a topological space that maps onto another space, preserving certain properties. It allows us to explore the multiplicity of preimages in the covering space and provides insights into the structure and connectivity of the original space. Overall, the chapter talks about the realm of topological spaces and explores connectedness, path connectedness, covering spaces, while talking about the fundamental properties of spaces in general. Moving on to topic 1.3, fields. A field, denoted as F, is a set that contains elements of any nature, such as numbers or other objects. It is equipped with two fundamental operations, addition and multiplication. These operations follow specific properties that govern the behavior of elements within the field. The first property is closure, which means that whenever we perform addition or multiplication on any two elements within the field, the result remains within the field itself. This property ensures that the field is closed under these operations. Associativity is the next property, which states that the order in which we perform addition or multiplication does not affect the final result. Regardless of how we group the elements, the outcome always stays the same. Commutativity is another important element of fields. It guarantees the result of addition and multiplication remains unchanged when we change the order of elements involved. The field also contains unique elements such as 0 and unit elements, denoted as 0 and 1 respectively. The 0 element acts as an additive identity, meaning whenever we add it to any element, the result is always the same. Similarly, the unit element serves as a multiplicative identity, ensuring that whenever we multiply any element by the unit element, the result is the original element itself. Every element in the field has a unique additive inverse, which when added to the element yields the 0 element. Likewise, non-zero elements possess a unique multiplicative inverse such that whenever multiplied by its inverse, the result is always unit. The final property is distributivity, which describes the relationship between addition and multiplication. It states that multiplication is distributive over addition, meaning that when we multiply an element by the sum of two other elements, it is equivalent to multiplying the element by each of the two elements separately and then adding the results. Fields play significant roles in complex numbers denoted as C, real numbers denoted as an R, while complex numbers form an algebraically closed field, meaning that for every non-zero polynomial equation with the coefficient C, it has at least one root in C. On the other hand, real numbers do not propose this property. That takes between two vectors and returns a scalar defines the properties such as linearity, symmetry, and positive definiteness. He then also discusses the concept of linear combination, which is the sum of vectors multiplied by scalars. Showing the linear combinations can be used to define subspaces, which are subsets of a vector space that are closed under the addition and scalar multiplication. Inner product spaces are in linear combination and basis sets. Kuprov then goes into more detail discussing the inner product spaces and discussing the properties such as orthonormal bases and projections. He introduces concept of a Hilbert space, which is a complete inner product space, and shows how the inner product can be used to define distances and angles between vectors. Koslov also discusses the concept of a basis set, which is a set of vectors that can be used to represent any vector in the space. He explains how to find a base set and shows how to use a base set to represent vectors as linear combinations. Koslov also introduces the concept of a dual space, which is the set of all linear functions on a vector space. Moving on to operators, superoperators, and representation of linear spaces. Koslov then introduces the concept of an operator, which is a function that maps vectors to vectors in the same vector space. He defines properties such as linearity and hermeticity and shows how operators can be used to define matrices. By also introducing the concepts of superoperators, he explains how superoperators are functions that map operators to operators. Koslov then discusses the concept of representation, which is the mapping of a linear space onto another linear space that preserves the structure of the original space. He shows how representations can be used to simplify calculations and solve problems that provide examples of provides examples of representations such as coordinate representation and basis representation. Operator norms and inner products. An operator norm is a way of measuring the size of an operator. Just as the magnitude of an operator tells us how long it is, the operator norm tells us how big an operator is. There are multiple ways of defining the operator norm, but one common way is the spectral norm, which is the largest singular value of the operator. An inner product is a way of measuring the angle between the two vectors. Specifically, it is the function that takes the two vectors as inputs and returns a scalar value that represents the cosine of the angle between them. The inner product is linear in its first argument, conjugate linear is in its second argument, and satisfies some other properties such as being. Matrices are often used to represent linear operators, but they can be also represented by vectors in certain cases. Specifically, if we have an operator A that acts on a vector space V and we choose a basis V, V1, V2, all the way till Vn for V, then we can represent A as a matrix by computing the action of A on each basis vector and collecting the results in the matrix. This matrix can be then used to multiply the average rotation to any vector in a 3D space by matrix multiplication. And the advantage of this representation is that it allows us to use linear algebra techniques such as matrix multiplication, Engine value decomposition, and singular value decomposition to analyze and manipulate the operator. Moving on to chapter 1.5, we have groups and algebra. Groups in algebra are the fundamental mathematical objects that are used to study symmetry and structure in many branches of physics, including quantum mechanics. A group is a set of elements that can be used to combine a set of rules, while an algebra is a vector space equipped with a product that satisfies certain properties. In context of quantum mechanics, group and algebras are used to study the symmetries of physical systems such as rotational symmetry of a molecule or the gauge symmetry of a particle. The symmetries of a system can be predicted by a group, and the operators that generate these symmetries can be predicted by the elements of algebra. Moving on to finite, discrete, and continuous groups. Groups can be classified into several categories, including the three I just mentioned. Finite groups have a finite number of elements, while discrete groups have a countable number of elements. Continuous groups have an infinite set of elements that form a continuous set. A conjugacy class and a centers. In a group, two elements are said to be conjugate if they're related to each other by similarity transformation. The set of all elements that are to conjugate to a given element is called the conjugacy class of that element. The center of a group is the set of elements that commute with all other elements in the group. Conjugacy classes and centers play an important role in the study of group theory. For example, the number of conjugacy classes in a group can be used to determine the number of irreducible representations of that group. The center of a group can be used to determine whether the group is an abelian or a non-abelian group. Groups, action, and orbit and stabilizers. A group action is a way of associating a group with a set of objects. The action of stabilizing on a set can be used to define the concept of an orbit and a stabilizer. The orbit of an object can be a group action is the set of all objects that can be obtained by applying the group elements to the original object. A stabilizer of an object is the set of the group elements that leave the object invariant. Group actions, orbit, and stabilizers are used to study the symmetries of physical systems. For example, the action of the group SO3 on a molecule can be used to classify the vibrational modes of the molecule. The stabilizer of a particular mode corresponds to the symmetry operations that leave the wet mode invariant. A matrix representation of a group is a way of representing the group elements by matrices that act on a vector space. Matrix representations can be used to study the systematic symmetries of a physical system. For example, the rotational symmetry of a molecule can be represented by matrices that act on a space of the molecule's wave function. Matrix representations of groups are also used in the study of quantum mechanics. The operators that represent the symmetries of the system can be represented by elements of a matrix algebra. The irreducible representations of a group that can be used to classify the states of a physical system. Orthonology theorems and characters. Orthogonality theorems and characters are tools that are used to study the representation of theory of groups. Orthogonality theorems can be used to relate the inner product of different irreducible functions of a group. Algebras and Lie algebras. An algebra is a mathematical structure consisting of a set of elements, a field of scalars, and a multiplication operation that satisfies certain axioms. For example, examples of algebra can be associative algebra, Lie algebra, and Jordan algebras. A Lie algebra is a vector space equipped with a binary operation called the Lie bracket that satisfies certain axioms. Lie algebras are an important tool in physics and other areas of mathematics and are used to study symmetries and conservation laws. The exponential and tangent maps are important for studying Lie algebra. The exponential map takes place an element of a Lie algebra and produces an element of the corresponding Lie group, while the tangent map does the opposite. It takes an element of the Lie group and produces the element of a Lie algebra. These maps play a crucial role in the theory of Lie groups and Lie algebras and are used to define the exponential and logarithmic functions on a Lie group. Ideals, simple and simplistic algebras. An ideal is a subset of an algebra that is closed under multiplication by elements of the algebra. Ideals are important because they provide a way of understanding the structure of an algebra by looking at its quotient algebras. A simple algebra is an algebra that no proper non-trivial ideals, while a semi-simple algebra is an algebra that can be decomposed as a direct sum of simple algebras. Simple and semi-simple algebras play a fundamental role in the theory of Lie algebra and are used to classify Lie algebras and their representations. Matrix representations of Lie algebra is a way of representing the elements of a Lie algebra as a matrix that satisfies the same Lie bracket relations as the original Lie algebra. Matrix representations are important because they provide a way of studying the Lie algebras using linear algebra techniques. In particular, they are used to define the adjoint representation of Lie algebra, which explains the crucial role in the theory of Lie algebras and their representation. Envelopes and complexifications and covers are important tools for studying Lie algebra and their representations. The envelope of a Lie algebra is the smallest Lie algebra that contains it as a subalgebra. The complexification of a Lie algebra is obtained by complexifying the underlying vector space, while the cover of a Lie algebra is obtained by taking the universal cover of the corresponding Lie group. These constructions are used to study the representations of Lie algebras and their properties. Cartan subalgebras is a maximum abelian subalgebra of a Lie algebra. It plays an important role in the theory of Lie algebras and their representations and is used to define the root space decomposition of a Lie algebra. The roots of a Lie algebra are the non-eigenvalues of the adjoint representation of the Cartan subalgebra, while the weights are the eigenvalues of the irreducible representations of the Lie algebra. The theory of Cartan subalgebras, roots and weights is used to classify Lie algebras and their representations. Killing form and the Casimir elements. The killing form is a symmetrical bilinear form on a Lie algebra that is used to study the structure of a Lie algebra and its representations. The Casimir element of a Lie algebra is an element of the universal enveloping algebra. Moving on to topic 1.6, the building blocks of spin physics. The chapter starts by explaining the concept of Euclidean and Minkowski spaces, which are mathematical frameworks for studying space and time. Euclidean space is a three-dimensional space with the Euclidean metric, while a Minkowski space is a four-dimensional space with the Minkowski metric, which includes the fourth time component. The next part of the chapter discusses the special orthonological group in 3 dimensions denoted by SO3, which describes the rotation of objects in a 3-dimensional space. The special unitary group in 2 dimensions denoted by SU2 is also introduced in the chapter. SU2 is a group of 2 by 2 unitary matrices with a unit determinant. Now, in physics, space is a fundamental concept that describes the physical environment in which all events take place. There are two main types of spaces: Euclidean space and Minkowski spaces. Euclidean space is the familiar three-dimensional space that we experience in our daily lives, while the Minkowski space is the four-dimensional space that is used in special relativity. Euclidean space is characterized by its metric, which is the distance between any 2 points in the space. This metric is given by the Pythagorean theorem, which states that the square of the distance between the 2 points is equal to the sum of the squares of their differences in the x, y, and z directions. The Minkowski space, on the other hand, is characterized by its metric, which is called the Minkowski metric. The Minkowski metric is defined in the terms of the square of the space-time interval, which is the difference between the square of the distance between the 2 points in space and the square of the time difference between those 2 points. Now, there's a special orthogonal group in 3 dimensions, denoted by SO3, and is a special rotation of three-dimensional space that preserves the distance between any 2 points. The group is defined as a set of all 3 by 3 matrices that satisfy the condition that their transposed matrix is equal to their inverse, whose determinant is equal to 1. The SO3 has many important applications in physics, particularly in the study of rigid body motion. Any rigid body can be represented by a point in space, and its orientation can be represented by a rotation in the SO3. The group is also important in the study of quantum mechanics, where it's used to describe the spin of particles. Special unitary group in 2 dimensions. The special unitary group in 2 dimensions, denoted by SU2, is a group of 2 by 2 complex matrices that have the determinant of 1 and a unitary nature. Unitary matrices are those that satisfy the equation or the condition that their Hermitian conjugate is equal to their inverse. SU2 has many important applications in physics, particularly again in the study of quantum mechanics. SU2 is closely related to the special orthogonal group in the 3 dimensions SO3, as the two groups are the same Lie algebra, which we talked about in the last topic. The relationship between the two groups is known as the spin-orbit coupling, which describes the interaction between the spin of a particle and the motion in 3 dimensions. The relationship between the SU and the 2 and the SO3 is an important concept in physics, particularly in the study of quantum mechanics. The two groups have the same Lie algebra, which means that they share many of the same mathematical properties. This relationship is known as the spin-orbit coupling and describes the interaction between the spin of a particle and its motion in 3 dimensional space. In quantum mechanics, the spin of a particle is a fundamental property that describes the intrinsic angular momentum. The spin of a particle can be used to describe the mathematical framework of SU2, while its motion in 3 dimensional space can be described using the mathematical framework of SO3. The spin-orbit coupling describes the interaction between these two frameworks, and it plays an important role in the study of many systems. The final topic in this chapter, 1.7, is linear time invariant systems. So linear time invariant systems are basically explaining the frequency and the pulse response of these systems, and the properties of the Fourier transform and the concepts of causality and the Hilbert transform. The chapter provides a thorough understanding of the mathematical foundations of these systems and their applications in various fields, including quantum mechanics. Moving on to the pulse and frequency response. So this chapter begins with the discussion of input and output signals of a linear time invariant system. The input signal is called the pulse response, and the output signal is called the frequency response. The pulse and frequency response are related by the Fourier transform. The chapter also discusses the convolution theorem, which relates Fourier transform of the pulse and the frequency responses. The chapter following this discusses the properties of the Fourier transform, which includes linearity, time shifting, frequency shifting, and modulation. They also discuss the Parseval's theorem, which relates the energy of a signal in the time domain to the energy of the signal in the frequency domain. Finally, the causality and the Hilbert transform, which talks about the causality being a property of a system that states that the output of a system at any time is dependent only on the input of the system at the earlier times, while the Hilbert transform is used to calculate the analytical signal of a real signal, which contains the phase and amplitude information of the signal. With this, we come to the end of the first chapter.